Okay, we're off and running. This should be Chem25EBlake, and it should be more Lewis structures. At the end of the list I gave you, I gotta go back here for a little bit because this is the last one we're sunk. Okay, we got 37, 46, 37, 48, 49. Okay, so we have BCl5, phosphorus tetrachloride. Okay, and then I'll just go back to the beginning of the 8 if we need to. Okay, PCl5. Okay, again, we'd have to give you this chemical formula, and you're trying to come up with the Lewis structure. Now, automatically, you can pretty much tell that phosphorus is going to be your central atom. And if there's 5 chlorine around it, each one bonded to it, and there's 2 electrons per bond, you can see that we have an expanded octet. We have 10. So I've got a phosphorus, a chlorine, a chlorine, a chlorine, a chlorine, and a chlorine. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And phosphorus is below the nitrogen, it has 5. 1, 2, 3, 4, 5. So we have 7 times 5 is 35, 36, 37, 38, 39, 40 electrons around your central, well, in the compound. So let's put phosphorus in the center. Whoops. Put a chlorine around it. Cl, 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 Cl. And I could put it up here just for the sake of being consistent with what I had in the notes. Let me see where I put it. Okay, that's where I put it, sort of. Okay. What they did then, there's not one right answer for this because it's a 3-dimensional thing. You could put it about where you want. They've got these 2 kind of scooched around like so. So now if I put my shared pairs in, I have that one, that one, that one, that one, and that one. Phosphorus already has more than 8. Put 8 on the chlorine total. 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Add them up. That's 8 times 5 is 40. We're done. We don't have to worry about charges. It's not an ion. We don't have to worry about double bonds or triple bonds. Okay, so it's just going to be replaced. Basically, you're going to have a Cl here, a Cl here, a Cl here, and then you're kind of going to split the difference on these guys. Then make sure the chlorine each have 8. 2, 4, 6, 8, 2, 4. Come on. 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. And that's what it would look like, phosphorus pentachloride. Well, actually, no. When we get into valence shell electron pair repulsion theory, this one would have trigonal bipyramidal shape. Well, I'm not sure if that's the way this book does it. Be bipyramidal maybe in this book. We'll see. Well, I guess I can delete this. We'll come back to that, by the way. I imagine I have those in the notes somewhere in that section. And then the last one there is SF6. This one would be bipyramidal. or hexagonal, I think, in this book. Whoops, we'll deal with that later though. SF6. Which means you have a sulfur and 6 fluorine. One, two, three, four, five, six, 7 on the fluorine. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. I have these jammed too close together. 1, 2, 3, 4, 5, 6, 7. 2, 3, 4, 5, 6, 7. And sulfur has 1, 2, 3, 4, 5, 6. So 7 times 6 is 42, I think. 44, 46, 48. Let's see, I did something wrong. 7 times 6, what did I do wrong? Okay. Okay. Yep, that's right. 48 electrons. Okay. So put my sulfur as a central atom. Yeah, I got a fluorine on the. I'm not sure how I drew this. I want to draw it the same. You could put 4 and then put like 1 in this corner and 1 here or something like that, or evenly distribute them. I imagine they're evenly distributed on this way. It doesn't matter. You're going to end up with the same answer. Yeah, I've got them evenly distributed over there. So just for the sake of notes, let me do it the same way. Put a fluorine above. Whoops, it's a little high up. Put a fluorine here and a fluorine here. Kind of split the difference on the others. Following the same steps each time. 2, share pair, share pair, share pair, share pair, share pair, share pair. Then give everybody 8. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. Then give everybody, replace it with sticks. So I have sulfur, fluorine, 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 fluorine. Then the fluorine, each make sure they get 8. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. 2, come on, 4, 6, 8. And that would be done. No chart. I forgot one step. Back here, you have to get 48 electrons. If you forget that step, you're likely to fall off the rails here. So you have 2, 4, 6, 8 times 1, 2, 3, 4, 5, 6. 48 electrons. So this would be fine. Okay. Where are we at on the next part? So let's go back to the beginning of this chapter for a little bit, since I've got some time on this video. Why do atoms bond? Well, you should know this from last year. What they are doing is, basically the universe went kablooey bang, and all the rules for how quarks are put together, and leptons and gluons and muons and pi mesons and all that to make your nuclei and electrons, to make your atoms. The rules are established. And so there are rules. You kind of ask the question, why are the rules the way they are? We're still working that one out. But we're going to follow some rules here. So why do atoms bond? The way the rules are, atoms are going to have a lower energy level, and they're going to be more stable when they have 8 valence electrons on their outer energy level, with the exceptions that we've just discussed. To get 8, they're either going to metallic bond, like two metals did from chapter 7, or they're going to give and take valence electrons to ionically bond, which was also in chapter 7, or they're going to share electrons like we're doing in this chapter 8 to get covalent bonds. When covalent bonds happen, we end up with molecules. I want to see something here. All right, there it is. There it is. This is the important one. Okay, the chemical bonds that results from sharing valence electrons is a covalent bond, and a molecule results when two or more atoms bond covalently. Now, I was just tweaking this next page here from the physical science class, but this page you really need to understand and know. For ionic bonds, you're going to have electrons given by a metal, taken by a nonmetal, and you're going to end up with an ionic solid that we will call a salt. There's hundreds of salts, I suppose. Sodium chloride is one of them. We call that one table salt. But anytime you have a metal with a nonmetal, you have a salt. Covalent bond happens when electrons are shared between atoms, and they occur between two nonmetals up in the corner. If you go back through all these examples, they're all nonmetals. Sulfur's a nonmetal, fluorine's a nonmetal, phosphorus is a nonmetal, chlorine's a nonmetal. You get the idea. They're all nonmetals. Even hydrogen that's up in this corner is still a nonmetal. It's the only nonmetal on this side of the table, but it's still a nonmetal. All nonmetals shared between nonmetals. That's covalent. And you get a molecule. Now, when two atoms are close to one another on the periodic table, they're likely to covalently bond because they have similar electronegativities. Most covalent bonds occur between nonmetals. Now, if you look at what I just said, is if they're close, they're likely to be covalently bonded, and most are between nonmetals. So can metals ever covalently bond? Oh, sure. Oh, sure. It's not real common, but oh, yes. Lithium, or anything in this column, can covalently bond with hydrogen. Anything in this column could covalently bond with hydrogen. These would make hydrides. So typically, these guys are giving, these guys are taking, and the ones in the middle, especially up in here, are often likely sharing. But it's not all that common, but you could have sharing happening all over the place. You could have give and take operating where you don't expect it in covalent bonds. And things that would normally covalent bond. But it happens. We've just, up to now, not been looking at all those exceptions. This is how we've been looking at it. Give, take, share, and that'll usually keep you out of trouble. Two atom diatomic molecules are more stable than individual atoms. Examples of diatomics are N2, O2, H2, F2, Cl2, Br2, and I2. Now, basically, they fall from N2O2, F2. I'm not missing one in my note. And down here. Here's where your diatomics are. There. And hydrogen up here. H2, N2O2, F2, Cl2, I2, Br2. That's where your diatomics are. Uh-oh, where's my eraser? Terms to know, a double bond. I've been using that term. You probably know it from last year. Nobody's questioned it yet. A triple bond, molecule, diatomic molecule, chemical formula, H2O is one. Molecular formula is the chemical formula of a molecular covalent compound. Let me see if I can come up with an example here, if I got room. Okay, well here's my H2, O2, and N2. Notice that my N2 has a double bond, N2 has a triple bond. O2 has a double bond, H2 is a single bond. Let me talk about chemical and molecular formula. See, if you have an ionic compound like calcium carbonate, that is a chemical formula. It is not a molecular formula because this is not a molecule. If you have H2O, you have a chemical formula. It is also a molecular formula because that's a molecule. N2 is a molecule, that's its molecular formula or its chemical formula. O2 is a molecule, this is its molecular formula or its chemical formula. Well, this is its molecular formula, and this is its molecular formula or chemical formula. So you don't call ionic compounds molecular formulas. I know, a little bit confusing, but let's go a little bit farther here. I think that's going to be a good place to end right there because the topic kind of changes.